So we were discussing moment curvature relationship. So in very brief, what it means is we are going a bit further than what we do to ensure ductility by using just the usual restriction on the strain of tensile steel to keep it in the tension control region. So if you all remember, um, in the ACI code, there is a strength reduction factor for flexural members, and that starts at, so when this is just your steel is barely yielding, so the strain in the most extreme tension fiber of steel is 0.002. So at this point, you have your ACI code allows you to use 0.65 as the strength reduction factor. So anything below this is a compression controlled failure. And this exact point is the balanced failure. You get crushing of concrete. You get crushing of concrete and yielding of steel at the same time. Now, so when your strain in tension steel is 0.005, then from this point onwards, everything is considered as a tension control failure. So it goes like that. I think you all remember this from the ACI code. And for tension control failure, it allows you to use 0.9. So if you remember in the recording, we watched a video of an under-reinforced beam failing. You can see that, okay, let me just show you both very briefly. We can watch and compare under-reinforced and over-reinforced beam. And in a second, I'm going to pull up the okay, while that pulls up, let's just continue. So that's what we did in the regular, in the first step or in the initial design. We need to at least ensure that in flexural members, we are having a tension control failure. That is, we are in this region, okay? So, but we will go a bit beyond here. Oh, okay. Let me reopen this file. Something wrong with the picture. Okay, just a second. Okay, so here, if you watch, this is for over-reinforced concrete beam. Now, okay, here is the loading. You can watch that the failure is going to be quite explosive and catastrophic. Yeah, you can see that's exactly where the failure took place. So you see when it crushed, there is like a sudden large deflection without any warning. So it's almost like a brittle material. This is what happens when you put too much steel and the tension steel did not yield when you're reaching your ultimate, when you're reaching your load for crushing the concrete. So when the concrete gets crushed, the steel is quite far from yielding, so you get a explosive, brittle kind of failure, and with a sudden large deflection. So you contrast that with the under reinforced, where you will have a slow progression of cracks. So you see the cracks developing there. I think they show a close up. So when the concrete starts crushing, you start getting cracking in the steel, and as you keep going, you keep going. So you see very slowly the compression, the concrete starts getting crushed in compression. You come and you remember the last one, it just went boom like that. So we don't want that kind of brittle failure. We are looking for a ductile failure. Okay, let me see what's wrong with this picture. Okay, just a moment. Let me open an older version just for the picture. Maybe it will show up there. Okay, here it still shows up. So okay, let's just go through here. Yeah. So when you have flexural members, they don't, as you see, when your moment capacity is exceeded, they don't immediately just collapse, as you saw the under reinforced beam. So what happens at this section is you get a constant moment hinge. That means at that particular section, you already reached whatever maximum moment you can carry, and it cannot carry any more moment. However, the steel is yielding, so it can maintain that moment and it can keep deforming. So it's like a plastic hinge. So what we mean is, you know what's a hinge, but this is a constant moment hinge. So this can carry the moment, but the material, the steel is just flowing as it yields. So so this behaves like a hinge in the sense that it cannot take any more moment, and whatever excess load you apply, it has to redistribute. Okay, so when you actually get collapse in a structure, you don't get immediate collapse with the failure of a section. So let's look here. Supposing this is a simple two-story portal frame. Somebody has done an experiment, and this is to show that some of you took steel design already. We did see the plastic analysis and plastic moment analysis for a steel. We did only up to continuous beams, but you know that um, when you reach your moment capacity at a section, when you reach your elastic moment capacity, sorry, plastic moment capacity, MP, in the steel structure, then it cannot carry any more moment. You get a plastic hinge there. And you further moment, it can still carry, but what slowly the degree of indeterminacy is coming down, right? So by using experiments, even in reinforced concrete structures, they have observed that plastic hinges do form, and we can take advantage of that in the sense that when you're applying load to the structure, your first sectional failure does not mean failure of the structure. It can keep taking load, keep going, and you get true failure only when it becomes a mechanism. For example, here you have one, two, three, four hinges start forming at uh, points one, the blue points one, and then they start forming at all these red points too. Then when all of these nodes turn into plastic hinges, that's when the structure actually fails. Um, so that means if you just design based on the sectional failure, you're ignoring a lot of reserve strength the structure still has available. And that's what we will be seeing in this topic. How do we take advantage of that reserve strength to make our design more economical? That means you know that it's still going to carry more load. So if you just reinforce with respect to sectional failure, you're probably providing more than what you need, because even after that section fails, it can redistribute and keep carrying load. But if you ignore that and just design based on all the individual sections, you're kind of over designing. So how can we take advantage of that? And how does the code allow us to take advantage of that? Let's see. Just for that picture, I had gone to that other file. For some reason, the picture was not open. Okay, all this was in the recording, but all right. So then we went over briefly what is curvature. So your curvature formula is the strain at any given depth from the neutral axis divided by y, the depth from the neutral axis. So how did we get that? That's very simple. That is just based on the classical beam bending analysis. So you take this beam as being part of a large circle, and this beam is an arc which is subtending an angle theta at the center of that circle. And so this purple line that you see is the neutral axis, and this does not change in length when you bend your beam, right? Everything above the neutral axis gets compressed, and everything below the neutral axis gets stretched out. So we know all of this from classical beam bending. So if you look at a fiber which is at a distance y below the neutral axis, then what's the deformed length of that fiber? R plus y times theta, right? And the neutral axis length is r times theta. It's just your S equals r thetas, this arc length formula. So before bending, everybody had the length r theta. Now your fiber here has the length r plus y theta. So after bending, what is the strain? Final length minus original length by original length, right? So that gives you y over r. 1 over radius of curvature is the curvature. This is nothing but phi, the curvature. So you get you substitute that, you get epsilon. The strain is y times the curvature, or curvature is given by strain divided by y. Okay. And this is just bending theory. I think you all remember it. If not, please let me know. I know some of you, I think you took the undergraduate reinforced concrete maybe many years back. And I know I'm not getting time to do individual recap for each of you. So maybe that's why quickly we are going over here. Now, there's something up with the pictures here as well. Okay, we can return to the old file in a moment. But anyway, we know that the strain at level y is y over r, as you just saw. So your stress at that level is nothing but elastic modulus times strain. So this is the Hooke's law. So you have E times y over r. So you have two equilibrium equations at this section. That is, at this section, you should have force balance and moment balance. So if you're having pure bending, there is no axial force there. So your total force on this section, let's draw how this section looks. That's the beam. And at this cross section, you can imagine that that's the neutral axis. And you have compression all above. And below neutral axis, you have tension. Right? So we will call this C, we will call this T, compression and tension. So we know we need to have force balance. So there is no axial force at any cross section. So C should be T. That means integral of the total force over this cross section must be 0. Or if you integrate the stress over the entire area, you should get 0. So stress is E times y over r dA. This should be 0. So your elastic modulus and radius of curvature are constants over the depth. So you pull them out, you get integral y dA is 0. And we know that this is the definition of the centroidal axis. So when you have homogeneous material and linear elastic behavior, then the neutral axis is same as the centroidal axis. Okay. Remember, you need to have a homogeneous material, and your material should be in elastic behavior all over the section. Okay, so you then in that case you can say that your centroid of this cross section, centroidal axis, is the neutral axis. So your next equilibrium equation is moment equilibrium. So whatever external bending moment you are applying, whatever bending moment is acting at this cross section, in other words, that should be equal to the external bending moment that you're applying. Okay, so whatever moment you are applying should be equal to the internal bending moment at this cross section. So what's the bending moment at the cross section? It's nothing but the couple provided by the compression and tension. So how do you do that? For at each level, you have a force. Your force is, let's say, dF. That dF is the stress at that level times the area of this strip dA. Okay, so sigma dA is the force, and what's the lever arm for that force? Y. So force times Y. So you integrate that over the entire area, you get integral sigma y dA. So you substitute sigma is Ey over r, then you get E over r y squared dA, or E over r integral of y squared dA, which we know that it is the second moment of the area about neutral axis or centroidal axis, and that is the moment of area, moment of inertia. Okay, so you get moment is equal to EI the times the curvature. Okay, and EI sometimes you can call it okay, EI is, let's just write in a different form. If you write curvature is nothing but d theta over dx, that is your change in slope with respect to distance. Okay, it's more accurately over ds, change in slope. So if this is the shape of your beam, what's the curvature? So you have some slope theta at this location. Now you travel across the curve, you travel across the curve for for a length of ds, and when you come to the next point, your slope is now theta plus d theta. So your slope has changed from theta to theta plus d theta over an arc length of ds. So this is phi curvature equals d theta over ds. So you can approximate that as d theta over dx, and you can further approximate that over a length as theta over L. Okay, so if you have constant curvature. Now, if you replace that, you have m is ei over L theta. So now this is your ei over ls, or rather this is, let's just make delta theta over delta L. So ei delta theta over delta L. So for a segment of length L, your ei by delta L, this is your flexural stiffness. Okay, so let me have the other file open so that we can see the pictures. Okay. Okay, so now we all recall the moment curvature relationships. So what is so now let's see how does a moment curvature curve, how does it look for an under reinforced concrete beam? Let's look at that. So you look at this picture, you have several points here, 1, 2, 3, 4, and so on. So as you observe from the moment curvature relationship, you can get an exact measure of the toughness or ductility of this beam. For example, if you have this whole curve for a certain beam, now you get the area under this curve. This will give you the toughness of that member, okay, at the level of the member. And the larger the area, the more ductile is your failure. Okay, so let's look at individual points here. So what is the first point? Point number 1. From 0 to 1, everything is linear. The section is uncracked. Okay, not even tensile cracking has happened at the bottommost concrete fiber. So everything is behaving elastically up to point 1. Okay, so let's go here. So this is, so in this case, we can use a transformed section, okay? We can transform this steel into equivalent concrete, okay? Because your section has not yet cracked. So what is the area of that equivalent concrete? N minus 1 AS. So if you recall, the area of this steel, let's say the area of the tension steel is AS, okay? AS. Then you want to apply the classical beam theory. So you convert all this steel to equivalent concrete. So area of AS should be turned into N times area of AS. This is the equivalent area of concrete. So very briefly, so do you all remember equivalent beam? Now, I didn't cover it in the recording. I was assuming that maybe you all remember, but maybe not. So we can, let me just explain very briefly. Okay, so here we have a beam. Now, when this is the cross section of the beam, again, when we draw this figure, when we draw the entire length of the member and then we just show the cross section, this is a section of, this is one section from the beam, okay? It is, if you look at the isometric view, then it is this section, that's what we are, this is the section that we are representing here. Always when we draw a section, that's the cross section that we are showing. Now, what is equivalent section? So you have this, right? Now, what do you have in your bending equation? So you have your first equation that you have is force balance, C equals T. So from here you have integral sigma dA is 0 over the entire area, right? So that means, what did we say? Sigma dA is what? Strain is y over radius of curvature. So maybe you're looking at a strip, some strip at a distance y from the neutral axis, then the strain at the level of that strip is y over r. So stress is E times y over r. But you observe, okay, when we have two different materials in the beam, then your elastic modulus is not the same, right? So you have to break this up into two parts. So E1, let's say I have two materials, material 1 and then material 2. So E1 y over r, this is dA. This is over the area of material 1, plus I also need to do a separate integral over the area of material 2. This is 0. And that's your equilibrium equation. Now, moment balance, you take the stress, that is, or sigma times dA is the force acting on this strip, and the lever arm is y. So integral of all those tiny moments should give us the bending moment or externally applied moment. So this is, again, sigma is E1 y over r dA in the area of the first material, and E2 y over r dA in the area of the second material, okay? And now you can again see in this case, for the homogeneous one, we just took out E as a constant, R is also constant, and then we could simplify the equations a lot, right? But here, you can see when we have two materials inside, we are unable to simplify the equations beyond this point. So what we can do is we can say, okay, I will rewrite this equation as E1 y over r dA plus this I will write as E1 y over r. Then this dA, I will make it E2 by E1 dA. So in other words, all I did is I multiplied and divided by E1 in this expression. In this expression, I just multiplied and divided by E1 and I rearranged it like this. But now what's the advantage? Here you have dA. Now here I have something dA, right? So that means for material 2, this is my beam. This is my material 1. And that's my material 2. What I can do is I can say that, let's say that, let's just, for simplicity to understand just this concept, let me just redraw. Imagine the steel as a strip. instead of individual bars. It doesn't make any difference. Everything still applies, but just so that it is easier to see. Okay, this is your steel. And that's our neutral axis. Now, what we will do is we will say this beam is equivalent to above this, everything is same. Below this, everything is same. Now, remember, what is dA? That all the strip areas that we have been writing here. For example, what's the area of this strip? Whatever is the width, that is B, times dy, right? The tiny area of this strip, infinitesimal area of this strip is, this rectangle is how? This rectangle is like this. The width of this rectangle is dy, or the depth is dy, and the breadth is b, right? So b times dy, that is the area dA. Now, what I'm going to do is, where at the level of this steel, I'm going to modify this steel, and I'm going to replace it by like that. So that means just in this area, I change this steel to the same material as concrete, okay? Now here, everything is material 1. Here, everything is material 1. But what's the difference? Just at the level of this steel, now this equivalent rectangle here is not of the same width as in the original beam. So in the original beam, if the width was B, here my equivalent B is going to be, this is material 1, this is material 2, E2 by E1. That's the modulus of 2 by modulus of 1 times B. So I'm stretching this out. Why I'm stretching this out? Because I want at every level, I want the same, I want everything to be same material, right? That's my first purpose. Let me just put this thing. I want, first of all, everything to be the same material. But then I don't want to change the mechanics of how the beam behaves. So I want at every level the same force. So if I have a strip, let's say this is my strip in the original beam, right? This is width B, and this is depth dy. What is the force I have? Force is stress times area, right? So that means stress is EY over R. E times strain, Y over R is strain, times dA. But what happens? The E is different because I have different material, but I want the same force. So what I know that the force in the new material is E2 times Y over R dA instead of being E1 Y over R dA. So now, so that I have the same force in this equivalent beam, I want the same force in the strip as in the original one. So because the stress is going to be lower. Why stress is going to be lower? I changed it to the original material, which has a lower elastic modulus. So that lower elastic modulus multiplied by the strain will give me a lower force. But so that I can get the force back up to how much it should be, I scale up the area, okay? So what I do is I rewrite this as E1 times Y over R, E2 by E1 times dA, right? So that means uh, I scaled up the area. I just, wherever I have a different material, you can see me for a moment. So wherever,
you mean that steel, because it's much stronger than concrete, that's why you're stretching up the area.
Samal, it is stiffer, not about stronger. It's everything we are doing is in
Stiffer, yes.
elastic range right now. So stiffer, okay? So
Yeah, I mean stiffer. That's why you make the area bigger than
right,
before.
right. Because what we want to still apply all the equations which we can use for homogeneous beam, right? But now the section is not homogeneous. So wherever you have the different material, you want to convert everything to same material. But you want to keep the same force at every level. That means you have to increase the width wherever you have different material so that the force is still same as in the original beam. So now what you get is, yes, Bryce.
Please, can you repeat the concept of transforming the section?
Yes. So again, let me draw one figure. Okay. So here is okay. Let's say that here we have a beam completely concrete. Okay, completely the whole section is concrete.
Can you share your screen again?
Oh yes, I'm sorry. Here you see this section is completely concrete. So here I can use my equation. Sigma is m y over I. Moment is E times I times curvature. Everything that I derived for my for my uniform material, whatever equations I derived. What are those? Those are this and this. Okay, those are my key equations. I can use that. I can use that no problem when I have same material. But what we are saying now, okay, so now we don't have the same material, but we have in this beam, for certain area of the beam, I'm saying that over here, everything is steel. So I have, or let's not say steel, I have here material 1, again material 1, but here I have material 2. Now, what did we say? I cannot write exactly the same equation, this equation, I cannot write because these were for uniform cross section. So, but I want to be able to use the same equations even for this non-homogeneous cross section. Then what should I do? I should convert this to an equivalent cross section. That means till here everything is 1, that's fine. Wherever I have material 2, I scale up the width. I scale up the width of this. So if the original width was B, then here I will give a width of just this part will have a width of B equivalent, which is E2 by E1 times B. Okay. So now in this beam, what is the what's the point behind doing this? Because you made everything to uniform material, but at every level, let's say at this level, maybe this level is at a distance y from the neutral axis. Okay, at every level, you made sure that the force at this level is still same. That means you're keeping all the mechanics the same. Force equilibrium will not change, moment equilibrium will also not change. Okay, your equations are exactly the same as before, but you can apply your uniform cross-section equations. Okay, so for this one, your equivalent width is E2 by E1 times the original width. So this is your equivalent cross-section, and this allows us to use all the equations for homogeneous beam. Okay, so in the mathematical form, what we are doing is when you write force equilibrium, your force equilibrium for the non-homogeneous beam has to be written in two parts, over the area of material 1 and over the area of material 2. But we say now we are converting material 2 to material 1 again by changing the width. So your dA in the region of material 2 became E2 by E1 times dA. Okay, so in other words, now this particular thing we will write as E1 y over r E2 by E1 b times dy. Okay, that's what it actually is. So what that allowed you to do is, now you can see that in the transformed beam, everything is integrated over the same material E1. Okay, so all this now still boils down to integral over the whole area E1 y over r dA. So now you can take out E1 common. You still have integral y dA is 0. So neutral axis is same as centroidal axis. Now that concept applies. Similarly here, when you convert this to an equivalent area, again you get the whole thing E1 y over r dA for your transformed beam. So this still becomes E1 over r, E1 I over r, right? So in other words, when we make this change, then we can still use all the old equations for a homogeneous cross-section. Bryson, you remember everything now? I mean, okay, I cannot hear him anymore. That's fine.
Yes.
Okay, great. Okay, so now all this was just to recall equivalent cross-section. Let's come back here. So from 0 to 1, we are going to use the equivalent cross-section, okay, or transformed section. So in your code, it is referred to as transformed section. So remember when you did all the calculations, you said that how do you get the effective moment of inertia? So it's some kind of interpolation between the uncracked section, that is uncracked transformed, and the cracked, right? So this, of course, in the code allows you to approximate as gross moment of inertia. So between IG and ICR, you have some interpolation to give you IE, right? But up to this point, everything is still I uncracked transform. Up to point 1, everything is straight line. Now, at point 1, the beam cracks. So like you saw in the figure, not in the figure, in the video, this is under reinforced. When does the first crack start appearing? Okay, so here, you see here the first crack started appearing. So what happened? And then you have many hairline cracks, and they travel up to the level of the neutral axis. Okay, now we went a bit too far. They are all traveling up. Everything happens in a split second. So they are all traveling to the level of the neutral axis. So from 1 to 2, you have no increase in moment. It's just the propagation of the cracks. So the cracks start at 1, then they propagate up to the neutral axis, right? That is the straight line from 1 to 2. You don't see any increasing moment in that time. Then now it is a cracked section. Okay, 2 to 3, or between 2 and 3, what will we do? Okay, let me draw. Let me do one thing. Since these 3 are not appearing there, I will just put them here. Okay, now I can take out this. Okay. Oh, I have one. Okay, so between 2 to 3 is what happens? Now you have cracked section between 2 to 3. So between 1 to 2, you're dealing with an uncracked section. So you can use this transformed section analysis. So between 2 to 3, your concrete has in the tension has cracked. So if you all remember the basis for flexural design, remember we ignore the contribution of concrete in tension, if you remember. So everything below the neutral axis is now useless. So from that point, you cannot use the transformed section anymore, or this transformed section. You need to use a new transformed section, because everything, all your concrete below the neutral axis has disappeared. Okay. So in the 1 to 2, your steel area, you do it this way. So we usually only denote the area that is jutting out or overhanging there, and we denote that by n-1 times area of steel. Okay, let me not do in this picture. Let's do it in a new slide. Do it in a new slide. So this is 1 to 2. Here is what is in 1 to 2. You have your section with the steel. Now you convert this to equivalent section, and at the level of steel you have 2 overhangs like that. So the area of these overhangs should be here. Your area of steel, area of all the bars together is AS, area of steel. Okay, area of tension steel. So if it is compression steel, you will put a prime. Okay, so here you will change that to n-1 AS. Okay, what is n? Remember, n is modular ratio, modulus of steel by modulus of concrete. Okay, why -1? Because like this. Now here is your steel, here is your original section, and this was your steel. So you need to change this steel area. What is this steel area? AS. You need to change it to N times AS, right? So you pull out all this area. Now you're left with 3 holes here, okay? And then you put your transformed area here. So your transformed area will be NAS. So you have NAS, but then you have 3 holes inside. Now you take a bit away from the NAS and fill back the holes, okay? What you need to take out AS from NAS to fill those holes back up with concrete. So you have a full section here, fully filled, and you're overhanging on the sides by N-1 AS, okay? So this is the section we will use from 1 to 2. Okay, then from, from 0 to 1. This is from 0 to 1. Then from 1 to 2, you already cracked. So that means your everything below the neutral axis, your concrete is useless. So you have steel now. Remember, concrete and steel are both in the elastic range. So we can still use the transformed section analysis, but the original section is different. So your transformed section will look like you have this, and then here your steel is N times AS. So now you don't need the -1 because you don't have any concrete anymore. And now I will give you the standard notations. I think you may.
Excuse me.
Yes, Brad.
What do you mean below neutral axis there is no concrete?
Yes, no, there is, but see here. Let's go back to the video. Can you see this? You can see my mouse on the screen, mouse arrow.
Yeah, sure.
Okay, so this is. I wasn't sure. Sometimes in the share screen you don't see the mouse arrow. Okay. So now you can see when. Let me put it. Okay, now you watch this crack. So the tension crack is opening up here. You see?
Yes.
And then it is moving, and many hairline cracks all along the length of the beam. They are all moving, but they stop at the neutral axis, right? Because from there it is compression. Concrete is compression. So under compression, it won't let those are tensile cracks. So they will stop at wherever the compression zone is, they will stop. Now, of course, they are not, the whole thing is not cracked. You have places where it is uncracked, right? As we discussed for your serviceability calculations. Some sections it is cracked, some sections is uncracked. But for our strength analysis, we take that everything below the neutral axis, the concrete has already cracked. So it is not effective in tension. Remember, this is one of the assumptions for flexural design in concrete.
Oh, yeah.
Okay, so that means everything below the neutral axis, the concrete is ineffective in tension. Okay, is already cracked. So now, in this section, we call this depth to the neutral axis as KD. Again, maybe when you took the course, I know some of you are international, maybe like for me, till I came here, I used to follow IS code. The details can be quite different. So maybe if you followed, but I know is only in, maybe some of you followed European code or some other code. But remember, concept is almost same. Some things are different, but concept is almost same, okay? The mechanics cannot be different. experimental empirical part, it could be a bit different, but still the aim is same in all the codes. Okay, so anyway, this depth to the neutral axis from the top, you call it as KD, and the lever arm, that is, what is the lever arm? So I will draw the forces here. So your compression looks like that. It's still linear. All the stresses are still linear, directly proportional to strain. Here you have Fs times NAS. Okay. Here you have your concrete, or let's just call that T. I'm sorry. Put those details later. T, tension force, and C, compression force. So you know, okay, C should be at the centroid. Centroid is at 1/3 the distance from the base, so C is here. So the distance between C and T, that is our lever arm, right? So that is called JD. So J again, D is effective depth from the top to the centroid of the tension steel. That is small d. Remember, total height is called H. All these symbols, at least for ACI code, they are same in every textbook. They follow the ACI 318, so it will not change. Okay, this is the lever arm JD, and as you can see, JD is D minus KD over 3. So 1/3, right? This is KD over 3, the whole D minus KD over 3. That is JD. That's the lever arm. So from 1 to 2, we will use cracked section. Okay. So from 2 to 3, what is 2 to 3? 2 to 3, the point 3 is the proportional limit of concrete. So this is your stress strain curve of concrete. Now this point, and from this point on, it is not linear anymore, okay? So up to this point also, it's only approximately linear, but more or less it is linear. From this point on, it deviates quite a bit from linearity. So when you cross this orange point, that is the point 3 in the moment curvature curve, your stress strain relationship for concrete is not linear. That means you cannot write sigma equals E epsilon. You cannot write this for concrete. You cannot write FC. Concrete stress is EC modulus times epsilon C. This we cannot write. Sorry, just a second. Okay, right? That means what does this tell us? That means we cannot use when we are not okay, up to that point we are still linear. So from 2 to 3, we can still use exactly same analysis what we used in 1 to 2. Okay, same crack section, same everything. Now come to 3 to 4. Three to 4. 3 to 4. Here, concrete is not linear anymore. So can we use sigma is my by I, m is ei times curvature? Can we use this in the region from 3 to 4? See, we already crossed 3 here. In the concrete, we already went into nonlinear range. So can we write stress equal to modulus times Hooke's law? We cannot. It's not linear anymore. That means these equations, the ones we derived for linearity, they cannot be used anymore from 3 to 4. Okay? So what will we do from 3 to 4? We have to consider the exact stress-strain relationship of concrete. So that means you have your no more equivalent section business now. Here is your steel. And in your concrete, we said, okay, so this guy is already in non-linear, right? So, okay, before that, 1 point, always remember, strains are still linear. So if I draw the strain distribution, it is still, everything is linear, okay? Okay, but stress, now, it may be something like, it is not straight, the line, something like that. And then for the steel, you have Fs, stress in steel, times As, okay? Then how do we find the neutral axis in the region from 3 to 4? Okay, so we need to know this stress-strain relationship for concrete. How to know that? We are going to use this modified Hognestad relationship. Okay, this is uniaxial. This is in uniaxial compression. And if you do your cylinder compression test and if you fit, it fits quite well, okay? So just make one change, please. Instead of 1.8 here, you use 2. So this epsilon naught, the print is not so clear. Epsilon naught is 2 times Fc prime by EC. That is this point, epsilon naught, okay? 2 times Fc prime over EC. Now, a bit later. Okay, so this is your this is the relationship we will be using. Now you can see that, hey, it's not right off the bat, it's already not linear, but up to that point, it's okay. It's more or less linear, okay? So how will you get your stress strain curve? So what is the concrete strain here? We don't know. So at this, okay, 0.4 is some intermediate point, okay? So how do you find this? 0.5 is for steel yielding. 0.4 is some intermediate point. For 0.3, proportional limit of concrete, this one you can take up to approximately 0.5 Fc prime. So at the 0.3, at 3, concrete stress is roughly 0.5 Fc prime. Up to here, you can take linear. Now, at 0.4, let's say we are doing it for 0.7 Fc prime, suppose, okay? Some intermediate point. So we know that concrete stress at this extreme fiber, we know this Fc is 0.7 Fc prime. So now we can, so we know what is the strain. If you're given your Fc, you can back calculate your EC, okay? So we know our EC as well. EC we know, okay? But we don't know the neutral axis and we don't know Fs. So how are we going to determine the neutral axis depth? So can anybody say? Let's call neutral axis depth as C. How are we going to determine C now?
Don't you get like the centroid and multiply by the area?
First of all, thank you so much, Mercy. That's what that will be very good. You're involving in the discussion. Thank you, and it clears up for everybody else. So you see, that's the whole point we were making. That okay. First point that you can take the neutral axis as a centroidal axis, that we cannot use anymore after 0.3. Okay, so up to 0.3 on the curve, remember the steel stress strain relationship is linear, concrete stress strain relationship is also linear. Only when everything is linear, we can use modular ratio, convert to equivalent section, and now we use everything. Neutral axis is equivalent to centroidal axis, and then sigma is my over I, all of those, right? All of these things that we wrote here for a okay, all of these things that we wrote here, this is for a uniform section. Whole section is made up of one material. Under that condition, we can use all these. Neutral axis is equivalent to centroidal axis and these equations for stress and strain. So remember, we can convert everything to equivalent material only up to 0.3. After 0.3, the stress-strain relationship is not linear in concrete anymore. That means we cannot write this. See, what were we using till now for equivalent section analysis? We were using modular ratio, right? Here. Modular ratio here. Modular ratio N times AS. What is N? N is modulus of steel by modulus of concrete, right?
Mhm.
What do we mean? That means Hooke's law is still valid. That means we can still write FC, stress in concrete, is EC times strain. We can still write strain in concrete. Still write stress in steel is ES times epsilon. But after 0.3, we cannot write this anymore. So our modular ratio concept of transform into equivalent section, we cannot use after 0.3. Did you get it, Mercy?
Yes, it makes sense.
Okay. So what do we do after 0.3? We need to now determine neutral axis. We go back to the fundamental equation, C is T. Force balance should still be valid. So what do we do for C? Now it's not a straight line, so you have to use the integral. So integral from 0 to C. So all the way, this is 0, all the way up to C. 0 to C, stress times area, right? So this is 0 to C. What is the concrete stress? It is, you use our Hognestad curve, FC prime times 2 times epsilon C by epsilon naught minus epsilon C by epsilon naught the whole square. This is our stress times B dy. Okay. Yes. Now, how do we simplify this? Your FC prime is common. You pull it out. Your B is breadth is common. Pull it out. Now you have integral 0 to, sorry, this is little c, not uppercase C. Okay. You have 2 times epsilon C by epsilon naught minus epsilon C by epsilon naught whole square times dy. So we need epsilon C in terms of dy. That's fine because your strain is all still linear. So at any y, let's say this is your y, right? And this is, sorry, let's denote this as epsilon C max, epsilon Cm. Okay, epsilon Cm. That's at the extreme fiber. Now at any fiber, it is epsilon C. Now from similar triangles, let me draw this a bit clearly. This is epsilon Cm and this is epsilon C. and this is at any depth y, and this is at a depth c, neutral axis depth. So from similar triangles, what can we write here? We can say epsilon cm by c should be epsilon c by y. Oh, sorry, my battery is running out. Okay. Okay. So, okay. So epsilon, that's just similar triangle, right? This is the small triangle and the big triangle. Okay, they are similar. So from here, I can write epsilon c is epsilon cm by times y over c. So now I plug this in. Fc prime b two times. So epsilon c is epsilon cm y over c over epsilon naught minus epsilon cm y over c by epsilon naught square dy, right? So now everything is c is a constant, so everything is a function of y inside. You can do the integral. You will get fc prime b and some expression in c, right? So this is some function, let's say chi of c. Okay. Now this is equal to the tension force. Okay, this is c. This is the uppercase C, compression force in the compression block. C should be T, right? What is T? Now T is, okay, now do we know the strain in the steel? This is at level of steel, epsilon T, strain in tension steel. Do we know epsilon T? We know, right? So do similarly, take similar triangle. Now what is the distance from neutral axis to the steel? D minus C. So we can write, let's go to new page. We want T. Now we know that the strain in the steel divided by D minus C is the maximum strain, compressive strain in the concrete over C. So that means epsilon T is right. So do we know this? Yeah, we know this because we are doing it for a certain stress in the concrete FC, which is 0.7 FC prime. And we have the modified Hognestad relationship, that is FC is FC prime times 2 times EC, this is at maximum, times epsilon naught minus epsilon cm by epsilon naught the whole square, right? So we have this. So if you plug in FC equals this, if you plug in FC is 0.7 FC prime, you can solve for equal to how much? You know this already, right? You got the number, not question mark. I mean, you know it. You know this number. So, I mean, we are going to solve everything for one example, but I'm just showing the procedure, okay? Now we know the strain here. That's what we said already. We know this epsilon Cm. So based on that, we will get your epsilon T. We know epsilon T as well. So now what is see, remember, up to this point, steel has not yet yielded at 4, right? Okay, so remember, for 3 to 4, we are assuming steel didn't yield. Okay, we are assuming that. We will know that when we calculate epsilon T. Epsilon T equal to, you will get some value, right? Now, if this is less than Fy over Es, then it is okay, not yielded, okay? If epsilon T is more than Fy over Es, it means that stress in steel you should take as Fy. Is it clear? Okay. Okay. So, okay, so now we know the stress in steel. So tension in steel is whatever Fs times area of steel. So now when we write C equal to T, what do we have? So we have Fc prime B, then some function of neutral axis C equal to Fs As. And in this equation, we know everything except C. So we can solve for neutral axis. Okay. Oh, I'm sorry. At this point, we don't know. We don't know C as yet. So we don't know the epsilon T value. Okay. So we don't know what is epsilon T as yet at this point. So we are assuming that not yielded. This is, we are assume this. Now we got C, right? Now we need to check. Now check how much is epsilon T and whether steel not yielded assumption is valid. Okay. If not, you need to go back, adjust the steel stress to Fs. Now we will solve the numerical problem, but I hope you're understanding. Okay. That's
Can you hold on a little bit?
Yes. So we went through quite a bit. So anywhere it is not clear, please tell me. Thank you, Abigail.
Can you go back to slide number 12?
Yes.
Okay, so I guess where I'm getting confused is where like the last line where it becomes like the squiggly C equals C.
Yes. Okay. I mean, I just it's just some function of C. Maybe it is maybe the squiggle of C could be it could be something like 4 times epsilon Cm C square over 3 minus something epsilon Cm square times or over C cube. There is epsilon not here, and some expression, it has all the terms are involving powers of C, right?
Okay.
So it's, or in other words, it is something like maybe A plus B over C plus, let's not use A, B, C, alpha plus beta over C plus gamma over C square plus maybe in the numerator delta C square, blah, 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 whatever, right?
Mhm.
So it is all in terms of C. So now in this equation, on the left side, here you have a big nonlinear equation in C, right?
Mhm.
Your only unknown is C here because you don't have any other unknown. Everything else is in terms of C, right?
Mhm.
Your Fs is also in terms of C. Um, so this will be a big nonlinear equation in C. So we just need to solve for C. Of course, we will not solve by hand. Let's put a note here. Solve using, maybe you can use MATLAB or Excel or something else, right?
Okay, that cleared it up. Thank you.
Okay, okay. Oh, one point I do want to mention here. It's good that Abigail brought it up. We can, if you want, for this, actually most of the things that we are doing in the course, if you like, you can completely code it. Okay, you can write your code, and maybe if you want the Excel, you want to use VB, Visual Basic, or something. You want to make a macro, um, or you want to make MATLAB code or MathCAD or something. And please, it is. I'm not saying. I'm not saying it's not my personal some kind of preference or suggestion. If you go nowadays, you go to any structural engineering firm, you join. You will not do everything using the a GUI based software. For sure, you have to do some kind of, either maybe sometimes the company, they already have their spreadsheets with the macros, you use that, they will give you, or sometimes they may have MathCAD code, but sometimes they may ask you also to develop something, right? Maybe a lot of times maybe they are using they are starting some new or some new structure for which the code was not made, so you have to make it now, right? So for example, when I joined PCA, they didn't have uh, software for retaining wall. They were still making, actually even now it's not there. I don't know why they scrapped it, but they were planning to do that. So somebody, the previous summer intern, for me it was full year internship, but the previous person had started it in MathCAD. So they asked me to go through it's a long, the retaining wall, the analysis itself is quite long. And then all the reinforcement design. So it's not that um, uh, uh, my preference or anything. It's very important to be more comfortable with the coding. Okay, and I think they are preferring, if at least in general engineering, they are preferring that one something which is totally applied, like maybe MATLAB or Octave or Mathematica, MathCAD, some applied thing where everything is built in and you just use all the tools there. So that you need to know one applied, or I think it's called high level application. And you also need to know something like C++, or that is low level, right? You write everything from scratch, not machine language, but like very close to machine language. So you need to know both, is what I understand. In at least in general engineering, it has come to that kind of. You all, of course, you all will not be looking for entry level position, so you will be looking for higher up. So it is useful. Okay, I just want to say. Okay. Where we stopped at point 4. Next is point Oh, now the picture shows here, but not here. Okay, just a second. Maybe I need to reopen it. Okay, let me do one thing. Okay, oh yeah. Okay, now let me close and open. Okay, that's good. Now it works. Oh, not yet. Okay, so we stopped at, oh, it's still not. Okay. Okay, let me try one thing. Hopefully. Oh, so strange. Okay, anyway, sorry for this figure mess up. I will just show you here and then switch back there to right. Uh, Now 0.5 is where the steel yields. Okay, so when the steel yields, then do you think the concrete would have been crushed? Now we are coming to 0.5. This is steel yield. So when the steel yields, has the concrete been crushed? No, because it is under reinforced, right? We are doing, we only design under reinforced beam. So uh, sorry. So now the steel is yielding. So we have, what is the stress in the steel? Fy. It yielded just now. Fy times As. This is the tension force T. Now concrete is also not yet crushed, but somewhere getting there. So this is epsilon C. So how do you find epsilon C now? Or let's say epsilon C max. So you have this is C, this is D minus C, and here this is the yield strain of steel, right? Epsilon Y. Just now it has yielded. And how do you find epsilon Cm? Just take epsilon Cm over C, similar triangles is epsilon Y by D minus C. So we can rearrange to solve for C. So this case is easier, right? So we, no, I'm sorry, not rearrange to solve for C. Now rearrange to solve for ECM in terms of C. Epsilon Y times C by D minus C, okay? We don't know C as yet, and we don't know ECM either, but we know epsilon Y, okay? Now what are we going to write? Our force equilibrium C is T. So what is C? C is, again, you need to integrate from 0 to C, or modified Hognestad curve. So Fc prime B 2 times epsilon C by epsilon naught minus epsilon C by epsilon naught whole square dy. Now, what is epsilon C? So epsilon Cm, we know it is something in terms of neutral axis. Now again, for epsilon C at any y, at any distance y, your epsilon Cm over C is equal to epsilon C over y. So your epsilon C is just y over C times epsilon Cm. So y over C times epsilon y times C by D minus C. So that becomes y by D minus C epsilon y. So that's your epsilon C. So we have epsilon C in terms of y. Now we are going to plug in epsilon C here in terms of y. So once again, you will get Fc prime B times some expression of C, some nonlinear expression in C. Now, T is FYAS. So write T equal to C. So T is FYAS equal to Fc prime B and you solve for C. Okay, now we got our neutral axis. So, okay, I'm sorry, at every point I've been missing something here. Okay, let's go back to, I've missed a point for each of these sections. So maybe I will write it in blue so that it stands out. Okay, okay. So we did up to 5. Okay, we did up to 5. So for each of the sections, so let's write it from here onwards. So for each point, we now know the neutral axis, C, T, etc. We know everything. So what do we need if we want to construct the moment curvature relationship? What do we need? Moment and curvature, right? So for point 1, let's go back, maybe I write at each point. So 0 to 1. So for point 1, how do you get the moment curvature relationship? So let's blue. So for point number 1, your moment will be just cracking moment, right? So point 1 is the point of cracking. So moment is cracking moment. What's the curvature for point 1? Curvature for point 1 is nothing but MCR over E times I uncracked transformed. Okay. So you got M and phi for point number 1. So we can construct our graph now. So we know M and phi for point number 1. Okay, we got point 1 now. Now we set point number 2, nothing changes. The moment doesn't change at all, but it just opens up. The crack just opens up. Hold on, please. PowerPoint is hanging. Okay. So we got point. Now point 2, we said the crack just opens. So for point 2, this is for point number 1. So for point 2, M is still MCR, but your phi is now it is the cracked section. So MCR by, sorry, this is EC I cracked. Okay, ICR. Now point 3. For point 3, okay. So for point 3, how do you find M? M is C or T. Now you found C, right? Or T, both are same. Times lever arm. What's the lever arm? Lever arm is T minus, you need to find the centroid of this C. Now you have a total, sorry, here I have to, ECM I write on the strain diagram. Here I have to write FC, the stress. Okay. So here is my lever arm. Okay. That's my lever arm. I call that L. So I need to find where is the centroid of this nonlinear region. And there is my C acting. From there to D is L. So I will write for point 3 C times L, lever arm. That's my moment. And phi, how do I get phi? Now I can take, I know the concrete strain here, ECM at C. So I can take epsilon CM over C. That's my curvature. Right? Remember we said curvature is equal to curvature is just the strain at any level divided by depth from the neutral axis. Okay. So we got point 1, point 2, we got point 3. Now point number 4, Okay, this is for 0.4, what we just wrote. I missed 0.3. 0.3 was still 0.3, everything was still linear. Yeah, 2 to 3. 3, everything is linear. So for 3, we can still write, how to write m for 3? M is C or T times D minus KD by 3. Okay, this is still the lever arm, still linear at 3. Then phi is, we can write your epsilon C over KD. Okay, now there is 0.4. All right. Now 0.5 is where the steel has yielded. You can do in the same way. So we will write M is nothing but C or T times lever arm, and phi is epsilon C over Cm over C. Okay. So from 0.5 onwards, what happens is, let me switch to that figure. Okay. Oh, I can't see here either. Okay. Let me reopen. Give me a second. Oh. Okay, that's fine. I'll just draw it. Let me restart and see if it shows up. Okay, now they don't come at all. Okay. I will just draw it. So what did we say? Your steel will have a stress-strain relationship like this. This is for the material, steel. Now, initially linear, then yielding, then there is strain hardening, and finally softening and failure, right? So where are we at 0.5? So 0.5 is the yield point. So this is the 0.5 on the curve. So let me draw in parallel the curve, okay? Let's draw the concrete 2 here, just so that you can get the full picture. Okay, what is 0.1? For 0.1, we are at cracking moment. So concrete stress strain curve is, again, it is not proportional. This is Fs, epsilon s, this is Fc. Like that. Now, for 0.1 was cracking, right? So here to here we came 0.1. We are here. So that means we are somewhere far away for steel, and for concrete also we are somewhere quite far, somewhere there. Okay, so we are here. Then cracking, just the crack opening. Crack opening. We don't change anything here. the steel stress, okay, the steel stress will go up slightly more. So let's say this is 1.1.1. Now for 0.2, the steel stress may go up slightly more, and concrete also may go up slightly more because we have lost some area. Okay. Now we are here. Now we go straight like that, and this is 0.2. Now we are at 0.3. So 0.3. Oops. Just a second. Okay. Okay, so now we are at 3 here. So 3 was the proportional limit of concrete. So 3 will be here. This is 3, and here you can take concrete stresses 0.5 FC or 0.7, 0.5 is okay. Okay, this is 3, 0.5 FC prime, and the steel will still be somewhere maybe there. This is 0.3. Then now you're in the nonlinear range. And this is 0.4. So that is some point in between. We said that let's take 0.7 FC prime. So that's at 0.4. And now the steel is also coming closer. This is 0.4. Then you have 0.5. That is yielding of steel. So 0.5 is exactly here. And 0.5 for concrete, we may be here, right? So FC prime is still far. Okay, so we have plotted up to here. Now from this point, your steel will yield. Okay, so I'm not yet showing the calculations, but just explaining. Okay, what will happen? So from this point, steel will yield. So you will have something like that, and let's say this is 0.6. And by the time, for sure, concrete has crushed. Okay, next point will be crushing of concrete. Okay, sorry, this will be 0.6, not this one. And for 0.6, we may be somewhere there along the steel. So this will be 0.6 where concrete is crushing. Now, let's call this as 0.7. So from here, concrete is losing the strength, but the steel is hardening. So we may go something like that. And then finally, your steel will rupture, your steel will break. So that may be quite far, okay? So we are going to calculate, hopefully today, I don't know if we can do all of it, but we are going to do at least till 0.5. Okay, 0.5 is uncracked transform section cracking moment. 0.2 is cracked section, 0.3 is proportional limit of concrete, 0.4 is some intermediate point in the nonlinear range of concrete, 0.5 is yielding of steel. So let's at least do till here. Here is one example. Okay, so so I think all this was also in the recording. That's where I was going to continue, but it's fine. We spent some time because it's maybe a bit involved. So till here, you are all very silent. Till here, everything is clear, or okay?
Yes, clear.
Okay. Thank you. Okay. Okay, so this is our example under reinforced beam. So do you all remember how to check whether this rho 0.005, how to check whether beam is tension controlled, how to check whether your reinforcement is within the tension control limit? Maybe let's go, let's do a recap. Let me take a new page for that. Let me actually use the slide from the undergrad course. This one. Oh, there is a. Okay, sure. I don't have it somehow. I will show you here. Now, if you remember, this is your cross section. So now you are having crushing in concrete. And at the point where you have concrete crushing strain is epsilon u, we always take as 0.003. Okay. At this point, your strain in the tension steel is less than epsilon y, then this is a compression control failure. Or let's put this way, this is over reinforced section. Compression control failure. Okay, so this will be, you remember the over reinforced, how it failed like an explosion, sudden, like that. That's how this will fail. Now, Now, when you have epsilon u, if you exactly get epsilon y at the same time, that is, the steel yielding begins exactly when your concrete crushes, then your uh, balance section still it is compression control. Or just to put as balance section. Okay. This is balance section. Okay. So what is your relationship between, or what is your maximum reinforcement ratio that you can have for balance section? This is your neutral axis depth. This is d minus c. So your epsilon u over c is epsilon y over d minus c, right? What is epsilon u? 0.003. Epsilon y for steel, all of you remember 0.002. For 60 ksi steel, yield strain is 0.002. So you have d minus c over c is 2 over 3. So that means d by c is 5 over 3, or c by d is 3 over 5. This is for balance section, right? So if you write c equal to t. Now, all of you remember Whitney compression block? Maybe not. I should have all this in the slides. Just a second. Oh, okay, I have everything here. Okay. Okay, yeah, let it load up for a second. This is all recap. Okay. So for balanced failure, or where is the Whitney block? Yes, okay. So this is your actual stress strain relationship for the concrete when your maximum compressive strain is your ultimate strain. Okay. So that means concrete is crushing. So for that case, that's how the compression block looks. But now you can take an equivalent stress block to simplify things. So you can take a block which is of a depth A, and A is related to the neutral axis depth as A is beta 1 times C. Now, if you remember, beta 1 is given by beta 1 is for less than or equal to 4,000 psi concrete, 0.85, and then you cut 0.05 for every 1,000 psi increase, right? Okay. So come here. Now, this is balanced failure, right? Just like we did. C by D is 3 over 5. Now, if you have, this is, don't worry about this. See this one. This is C by D is 3 over 8. That's for tension control. This was the old code, but you can see this one. C by D is 3 over 8 for tension control. And that's how the reinforcement, that's how the strength reduction factor looks. So below epsilon y, everything is compression controlled. You have a big penalty on 0.65. For tension control, 0.9. Okay. Okay. let's come back. Okay. C over D is 3 over 5. So if you write your if you write C equal to T, you get from the equivalent compression block 0.85 Fc prime. A times B is tension is ASFY, right? Tension force. So, okay, back to there. I hope what we are saying is instead of taking the complicated nonlinear curve, you can take it as uniform stress here, that is gamma Fc prime, right? You can take it as uniform rectangular stress block. That will make the job much easier. Of course, this is all from the undergraduate course. So this is all, it's all familiar to you all, right? You all remember all these things, right? I mean, at any point, if you, these are all, you already, these are too familiar and I'm maybe just wasting time, you can tell me to stop and move ahead, okay? Okay. Just only request is please don't be completely silent. Then I don't even know what's happening. Okay. Okay. Still you are silent. Okay. 0.85 Fc prime AB. This is AS times Fy. Okay. So now Fc prime A is beta 1C times B is ASFY. So C is 3/5 of D. 3/5 of D times B. This is ASFY. Now you rearrange this, you will get 0.85 Fc prime over Fy beta 1 is equal to AS over BD. Is it clear? So,
Can you repeat?
Sorry, I missed the 3/5. Just a second. 3/5 beta. Yes. So which one I should repeat? Just the rearranging?
Yeah. No. I don't know. I can confuse them.
Like this. Okay. I think maybe you have forgotten slightly. I'm sure that's the reason. Now forget all the numbers, okay? Just see here the concept for a moment. Forget all the numbers.
Okay.
No, Bryson, see, this is beam, right? This is beam.
Yes.
Now, concrete beam. And here is your rebar, right? Now, when you load it, you want ductile failure. See, in the building, let's say when it reaches the ultimate load, you don't want it to break like a glass, right? Then everybody will just lose their life. No one, you cannot do any evacuation, nothing, right?
Yes.
Everything will just collapse like a explosion, right? But if you have good ductile failure, it will slowly collapse, right?
Yeah.
So you have enough time. Okay, you need to do this procedure, emergency, rush out. So at least you saved the lives, right?
Yeah.
Okay. So when will you have the kind of doom, that failure? See, you saw here. Let's go back to the video. This is under reinforced. Let's go back to over reinforced, okay?
Yes.
Okay. So see, you're loading. Maybe there is sound, maybe sound. Anyway, you cannot. I need to do something for the sound. Just a second. and then loading, 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 loading. And then okay, still loading, loading. You don't see much of anything. Oh, oh, that's why. Okay, see from here. We are loading, 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 loading. Now, damn. See how it failed? Did you see? It's
Yes.
okay. It's almost like an explosion. That means
Yeah.
when you put too much tension steel, when you put too much tension steel here, then what happens is, okay, if I put more and more steel, Bryson,
Yes.
if I put more and more steel, what happens to my neutral axis? It will go down, right? I'm packing more and more material downstairs, so my neutral axis will go down, right?
Yeah.
Okay. So when I have epsilon u 0.003, now let's say I put so much steel, I really pushed my neutral axis down. Now it will be something like that. Now when I get crushing strain in the concrete, this steel strain will be very small, right? It's less than yield strain. Did you catch it? Hello?
Yeah.
Okay.
Yes.
Yes. So it is okay. Sorry, I put a little bit down here. Here, that's the yield strain at the level of steel. I push down the neutral axis. So my steel strain is very tiny, less than or epsilon t less than epsilon y. So this steel has no chance to yield. When the concrete is crushing, that will control the failure, like boom, right?
Yes.
We don't want that. So what if I reduce the steel, and the neutral axis is moving higher and higher until I came to a point where when I get epsilon u of 0.003 in the concrete, at the same time I get epsilon t of 0.002, that is the yield strain in the steel, right?
Yeah.
This is balanced. So balanced means exactly when concrete crushes, steel starts yielding. We don't want that too, because that's just barely making it, right? We don't want that. Now ACI code is recommending that you must have tension control failure. That means for tension control failure, that is to get your maximum strength, you must, or that is to get the maximum allowable strength, when you have 0.003 crushing in the concrete, your steel strain must be at least 0.005. Okay?
Yeah.
Okay. So that means, so for balanced, we have 3/5, right? So for tension control, this is for balanced. AS by BD is reinforcement ratio. So rho B for balanced is 0.85 FC prime by Fy, 3/5 of beta 1. Okay?
Yes.
Now for tension control, for tension control, draw 0.005, everything remains same, 0.85 Fc prime by Fy. Now you have 3/8 here and then beta, okay? Is it clear?
Yes.
Okay, okay. Okay, so now let's check whether our beam is under reinforced. So what is 0.00, 0.005? 0.85 beta 1, 3/8 Fc prime by Fy. Now my request is always in this kind of class when we are solving any problem, I think you also take your calculator and solve with me. Only when we see the numbers, we start getting a grip over things. So 0.85 beta 1 is Fc prime is 4000 psi, so beta 1 is 0.85 times 3/8 times Fc prime is 4, Fy is 60, so you get 0.018. Is it clear? Okay, 0.018. Okay, now now what is our reinforcement ratio? We have 3 number 8 bars, so go back to just a second. Hello, Dr. Amur. Next week, no. Next week, no. Yeah, I will remove it. The 11 to 2. I wasn't sure how to remove only certain blocks, but I will. hello everyone. Actually, I have some urgent things. There is some mistake in something, so we have to stop here. But we will continue the problem. I may do either recording or we will continue it by next class. Okay, I may do a recording to complete it. Okay.
Right.
Okay. Okay.
All right.
Okay. Thank you.
Thank you.
Okay. Thank you.
Thank you so much.
Thank you. Bye bye.
Thank you.
Thank you, Dr. Nate.